Well, hello, good people. Today we are talking about electrostatics. This is the first day of our new unit on Unit 10, which is all about electricity. Now, when you think electrostatics, my hope is that what pops into your brain is static electricity, which is exactly what we're going to be talking about today. Electro normally has stuff to do with electricity. Statics means not moving or at rest. We're going to look at electricity that's not moving. This is opposed to electricity that is moving, like if you had like a current in a wire. You have a bunch of little charges all marching together in a line, but that's not what's happening here. What you have happening here is things just sitting still. That's electrostatics. Like if you had something that was charged positively or charged negatively and was just sitting there, that would be an electrostatic sort of situation. When we talk about electrostatics today, we have two topics that we are going to discuss. The first topic is going to be charge. And the second topic is going to be charging. First, that's this. I just wrote the same thing twice. First, we're going to talk about charge, which is like what is charge. That's pretty much going to be a review for you. We'll talk about positive charge and negative charge. Then we'll talk about charging, which is how do you actually give an object a certain charge, either a positive charge or a negative charge. Let's go ahead and get started here by talking about charge. When it comes to the topic of charge, we'll move through this real quickly here because these are all things that you already know. When it comes to the topic of charge, here's some stuff that you already know about charge. Here we go. Charge comes in two types. We say that there is positive charge and there's negative charge. Positive charge is carried by charge carriers, which we call protons. And negative charge is carried by electrons. Protons have positive charge, electrons have negative charge. We say that protons have positive charge the same way that we say they have mass. It's just something that they have. Electrons have negative charge the same way that they have mass. It's something that they have. So protons carry positive charge, electrons carry negative charge. Now, the next thing that you need to know about charge is that charge, I almost forgot this. This is something that you already know, is you know that when it comes to charges, we say that like charges repel and opposite charges attract. We say that a little positive charge next to a little positive charge says, no thank you, I don't like you very much, and they'll push each other away. Same thing with a little negative charge next to a little negative charge, they'll push each other away. But if you have opposite charges, like a little positive charge next to a little negative charge, they'll pull towards each other. Opposite charges attract and like charges repel. That's something that you know. Here's another something that you know, is that generally speaking, electrons are the ones that are free to kind of roam about. Protons a lot of times will be stuck in their atoms. They're kind of trapped. Electrons, especially valence electrons, they kind of have some freedom to leave their atom and kind of go wandering around. Protons are stuck in the nucleus of the atom, so they don't have much freedom. So in all the situations that we're going to look at, especially when we get to charging, you're going to see that the protons stay stationary and the electrons all move around. One more thing. There are two adjectives that we're going to use to describe charge. The first adjective that we're going to use to describe charge is we're going to say that charge is scalar. That means that charge does not have a direction. Most students would say, yeah, charge doesn't have a direction, but then they get confused when we talk about positive charges and negative charges. Because they say, oh, so positive is like backwards or positive is like forwards and negative is like backwards. No, don't be goofy. Just because we have positive and negative does not mean that we have direction. Charge is scalar. And the second thing that's true is that charge is also described by a word called quantized. Charge is quantized. What it means for charge to be quantized is that charge can only come in whole number multiples. Here's what that means. It means you could have 3 electrons worth of charge, or you could have 4 electrons worth of charge, or you could have 5 electrons worth of charge, or you could have 5 million electrons worth of charge. But you can't have half an electron worth of charge. You can't have 1.5 electrons worth of charge. You can't have 4.3 electrons worth of charge because it's impossible to have 0.3 of an electron. It's impossible to have half an electron. So any charge that you have has to come in a whole number multiple of electrons. This concept of charge being quantized is going to lead us to an equation eventually here, but before we get there, we have a few other concepts that we need to talk about charge. For example, the units of charge are coulombs, represented with a capital C. That looks like a lowercase c. Let me try again. Represented with a capital C. And the symbol that we use for charge is the lowercase letter q. So if I wanted to talk about how much charge an electron has, I would use the letter Q with a little subscript E for electron, and I would say the amount of charge that an electron has is equal to 1.602 times 10 to the negative 19th coulombs, because that is true. Check out my units here, check out my symbol here. If I wanted to talk about how much charge a proton has, I would say that the charge on a proton is equal to 1.602 times 10 to the negative 19th coulombs. Notice, once again, my units here, and I use the symbol Q for charge. You'll see here that both an electron and a proton have the same amount of charge. The only difference here is the sign. We say that electrons have negative amounts of charge and protons have positive amounts of charge. And that is true that an electron carries negative charge and a proton carries positive charge, but they carry the same amount of charge. Now, this is the point in the story where a lot of students say, wait a second, you're telling me that one electron has 1.602 times 10 to the negative 19th coulombs? Why didn't we just say that one electron has like negative 1 charge? Wouldn't that be like so way super simple? Yes, it would be super simple. Here's the issue, and this issue is going to come up again and again and again and again when we talk about electricity. The issue is that we discovered electricity before we discovered electrons. Like, before we knew what an electron was, we knew how current worked and how current could flow through a light bulb and make a light bulb light up. So we established all our units knowing things about current and how light bulbs light up, and we established all our units, and then all of a sudden later we were like, OMG, wow, look, I found an electron. And we were like, oh, wow, that's so cool. What units are we going to use to talk about its charge? And they were like, we're going to use the units that we've been using this whole time for charge, coulombs. And that means that an electron is going to have 1.602 times 10 to the negative 19th coulombs worth of charge, which is a very inconvenient number, but at that point the units were very well established. And so we carry on with our lives. This number, 1.602 times 10 to the negative 19th coulombs, is such a significant number that oftentimes it gets its own signal. And we label it with, or own symbol, we label it with the lowercase letter E. E stands for electron, meaning the charge on an electron is 1.602 times 10 to the negative 19th coulombs. We call this negative E if it's for an electron and positive E if it's for a proton. But the number is the same, so the E stays the same for both. This leads us to our quantization equation, which looks like this. We say that the total amount of charge that an object can have is equal to the number of extra electrons, or the number of extra protons, times the charge on one of those extra electrons, or one of those extra protons. Q total equals NE. This is the number of electrons times the charge on one. This should make some sense to you. That means that if something has 5 electrons, it has 5 times 1.602 times 10 to the negative 19th coulombs worth of charge. If something has 17 electrons, it has 17 times 1.602 times 10 to the negative 19th coulombs. This is what we mean when we say that charge is quantized, is we mean that it only comes in whole number multiples of E. You can't have a half of an electron. N always has to be a whole number. And this equation is worthy of your bag of tricks. Whoa, let me fix that. Take 2. Come on. Okay. There we go. Okay. Last concept before we can talk about charging, we have to talk about this concept that we call the law of conservation of charge. Now, if I told you, hey, what's the law of conservation of charge? My guess would be that you could tell me, oh, did I lose my pen? The law of conservation of charge. My guess would be that you would be able to tell me, if I asked you what's the law of conservation of charge, you would be able to tell me exactly what it is. My guess is that you would be able to say, oh, yeah, that means that charge cannot be created or destroyed. And that is absolutely true. Oh gosh, here we go. Oh gosh, okay, we could do it. Okay, charge cannot be created or destroyed. This is the law of conservation of charge. Here's what it means, is that charge cannot be popped into existence or popped out of existence. If I have something that's charged with 5 coulombs, those 5 coulombs had to come from somewhere. Something else had to lose 5 coulombs in order for that thing to gain 5 coulombs. We can shuffle charge around, like I could move positive charge from one place to another or move negative charge from one place to another, but I can't just snap my fingers and have something all of a sudden be 5 coulombs worth of charge or have 5 coulombs worth of charge. Charge cannot be created or destroyed. I can't snap my fingers and charge will pop into existence. I can't snap my fingers and charge will pop out of existence. If something's going to be charged, I have to take that charge from somewhere or give that charge away. This means that the total charge of the whole universe is always constant. You don't have any new positive charge being added, and you don't have any new negative charge being added, and you don't have positive charge being taken away, and you don't have negative charge being taken away. Charge cannot be created or destroyed, so however much charge we have right now is the amount of charge that we have. The universe is not getting more positively charged, and it's not getting more negatively charged. It is staying the charge that it is. And that law of conservation of charge is going to be the guiding principle for our whole next portion of our class today, which is all about charging. Let's go ahead and add a little new document for ourselves. Next, we are going to talk about, let's change up our color here, charging. We'll do it in green. Charging. When we're talking about charging, we're talking about a way for something to be either positively charged or negatively charged. We're talking about how are we going to move charges around in order to make something positively charged or negatively charged. Again, we're going to follow the law of conservation of charge. So charge is not going to pop into existence. It's not going to pop out of existence. It's going to stay where it is, but we can shuffle it around a little bit. So the question of charging is, how do we shuffle around charges? Well, we're going to talk about today 3 methods of charging. I'll put 4 on here, but I'll explain to you why one of them is completely invalid, even though I am going to put it up here. We'll talk about 4 methods of charging that you can use to make something either positively charged or negatively charged. The first method of charging that we're going to talk about today is friction. You have charged something with friction before. If you have, you've charged something with friction before. If you've taken a balloon, rubbed it on your head, and then held it out in front of you. Then all of your hair went and sticks up like a little lion. Why does that happen? Well, because of charging by friction. Charging by friction happens when you literally strip the electrons off one material and put them on another material by creating friction between those 2 objects. Here's the truth, is that not all materials have the same affinity for electrons. So some things like electrons more than other things. You knew this, you studied this last year when you studied chemistry and you studied the periodic table. You learned when you looked at the periodic table that you could track electronegativity, which is how much a certain atom likes electrons, how tightly it's seeking for electrons, or how tightly it'll hold on to electrons. We say that it's more electronegative, or that it has a higher electron affinity. Then something that's down in the bottom corner of the periodic table, we say stuff down in the bottom corner of the periodic table really just wants to give up electrons. It's hoping to rid itself of electrons. It is really not about those things. So different materials have different amounts of electron affinity. That means that when I take 2 things that have different electron affinities and I put a little friction between them and I strip off the electrons will leave the thing that doesn't really like electrons that much, and they'll attach onto the thing that likes electrons more. Let me show you an example. Here. Sorry, I lost my materials, but don't worry, I found them. Okay, here I have a black strip here. Oh, okay, yeah, you can see it. Here I have a black strip, and here I have a piece of wool. If I take this black strip and this piece of wool, this black strip actually has a greater affinity for electrons than the wool does. So when I charge this thing by friction, I gotta go this way. When I charge this thing by friction like this, I am literally stripping electrons off of the wool, and they are transferring to the black strip. That means that the black strip now has a negative charge And the wool now has a positive charge. Hey, do you see how we're following the law of conservation of charge here? This thing just gained a negative charge, which means this thing just gained a positive charge. I had to transfer charge. I moved charge, but I didn't create or destroy charge. This thing is now negatively charged. This is in contrast with, wait for it. Oh, wow, you can hardly see this. This is a clear acrylic strip here. Here I have a cotton cloth. The truth is that the cotton cloth has a greater affinity for electrons than the clear strip, so when I get this thing charged like this, I am literally stripping electrons off of the clear strip and they are going onto the cotton cloth, so the cotton cloth ends up negatively charged and the clear strip ends up positively charged. That is a little bit on that. Okay, that's charging by friction. Now, let's talk about what happens when you charge something the second way. Now, here's the thing. If I were to put this up on the board or up on my screen here, and I were to say, this is my second method of charging, and someone were to walk in here and they said, that's your second method of charging, they would get very mad at me. They would say, that is not a method of charging, Miss Wilson. That is what they would say to me. Because the truth is that this second method of charging is actually not a method of charging whatsoever. Because as you're going to see, it's not going to add charge or take away charge. The second method of charging is what we call polarization. And now I'm going to attempt, and I haven't tried this yet, so we're going to see how this goes. Okay, I'm going to attempt to show you a little demo here on my table, but I have to move all the things out of the way. This is my charger cord. Don't you just love how real and raw these videos are? Oh, so fun. You just get to see the truth all the time. Okay, we're going to see if we can get this to work. Okay, hi. Okay, here you see that I have a aluminum can of mango nectar. Yay! Here's an aluminum can of mango nectar. Here is a PVC pipe. This is a party trick which is sure to work for you. The next time that you go to your party with your PVC pipe, bring your PVC pipe with you. Then take a nice cloth here like this one. You will get that cloth, or you will get that PVC pipe nice and charged up here. Here's the truth is that this PVC pipe has a greater affinity for electrons, and this cloth has a lesser affinity for electrons. So what happens is when I go like this, I charge this thing by friction. I give the electrons up from the cloth. The cloth is now positively charged to the PVC pipe. The PVC pipe is now negatively charged. And now, check this out. Okay, we'll see if we can do this here. I take my little can like this. I put it on my table. I take my PVC pipe, and here is the party trick, which is sure to revolutionize your social life to make you look so cool and impressive in front of all your friends. Take your little PVC pipe, hold it next to your little can, and watch what you can do. Come on, buddy. You can do it. Let me get a little more charge on here. You do have to recharge your PVC pipe occasionally. Okay, come back. Here we go. Ah, yeah, there we go. That's pretty nice. Oh, come back, come back, come back. Can you do this at home? Yes, absolutely. Can you do this at a party? Yes, absolutely. Now, here's the question is, how is this little can being pulled towards this PVC pipe? Well, the answer, oh gosh, the answer lies in polarization. Here's the idea. This thing, this PVC pipe, we know is negatively charged by friction. But what's the charge on my aluminum can? It's neutral. But you say that's very interesting, Miss Wilson, because that doesn't seem to work. Because you say, I know that negative charge and positive charge pulls towards each other. But this thing is neutrally charged, so why is it pulling towards the PVC? Well, here's the truth, is that polarization is occurring. We don't call this a method of charging because the charge on the aluminum can actually stays the same the whole time. But the arrangement of charges inside the can is going to change. Allow me to draw you a little picture after I adjust everything back to the way that it was before I moved everything all around. Okay, yes, and we are looking good. Okay, great. Allow me to draw you a little picture of some polarization action. Here's what I have. I have my PVC pipe here. Oh, please do ignore the bells. I have my PVC pipe here, which is negatively charged. I bring it close to my aluminum can, which is neutral, like this. Now, this aluminum can has protons and electrons in it, so it has charges, but right now they're just all canceling out, and so there is no charge. What happens when this PVC comes close to this aluminum can is the electrons in the aluminum can look at the electrons over here and they say, excuse me, what are you doing over here? And the electrons in the aluminum can are repelled. So the electrons in the aluminum can run over to this side of the aluminum can, leaving behind their little positively charged atomic homes. So the protons stay where they are, stuck in the nucleus of their atom. Those electrons, they have some freedom to move. They run onto the other side of the can. This is what we call polarization, because now the can has two sides. It has a positive side, a positively charged side, and a negatively charged side. Notice that the net charge on the can is still neutral. I drew 4 protons and 4 electrons here to show that, but the can has a positively charged side and a negatively charged side. The moment that I move this the moment that I move this PVC pipe away, this thing, all the electrons are going to redistribute and it'll go back to being totally normal again. But for right now, it is polarized. When this thing is polarized, now the positive side of the aluminum can is facing the negatively charged PVC. And positives and negatives like each other, so the aluminum can will move toward the PVC this way. And that's how this party trick works. Now, before we can talk about the third and fourth method of charging, we have to talk a little bit about 2 different types of materials here, because there are 2 different types of materials that can experience polarization. One type of material that can experience polarization is called a conductor. The other type of material that can experience polarization is called an insulator. A conductor is a material typically that's made of metal. We call it a conductor because it's good at conducting electricity. It's also good at conducting heat. And so thermal conductors are normally good electrical conductors. But a conductor is normally made of metal. And a conductor has very free range sort of electrons. The electrons in a conductor are kind of free to go where they please. The parenting style of the little atoms that live inside of a conductor is a very free range kind of parenting style, like, yes, why don't you just go over there, go out, have fun, play, go to the playground, go wherever you want, come back home sometime if you want to. That's really kind of how things go in a conductor, is the electrons just kind of get to swim around and go where they please. In an insulator, though, it is not so. In an insulator, the parenting style of those little atoms is much tighter, where they say, excuse me, little electron, you said that you want to leave? Where are you going? You're going to the park? Who's going to be there? What time are you going to be home? Are there going to be other parents there? What parents are going to be there? What friends are you meeting? Oh, you know what? No, I'm actually just going to come with you. You know, you're not leaving my side. We are going to stay together. Yes, you are never leaving. And that's the parenting style of an insulator. So the little atoms inside of an insulator hold on to their electrons very, very tightly. They don't let them drift away from the atom. But in a conductor, the electrons kind of have some freedom to move. You can see this because here, the electrons inside of this conductor, inside of this aluminum can here, when I brought my PVC close like this, the electrons just ran on over to the other side of the aluminum can, and an insulator not so. However, an insulator can still be polarized. And you know that this is true if you've ever taken a balloon and rubbed it on your head like this, then take that balloon and put it on the wall. And you'll see that the balloon will stay on the wall. Why will the balloon stay on the wall? Because the wall gets polarized. Now, you can do this on your drywall at home. Is drywall a conductor? No, it's an insulator, but it can still be polarized. Let me show you how this happens. Let's say that you bring your, oh my, gosh. Okay, perfect. Let's say that you bring a little balloon. You charge it by rubbing it on your head. That little balloon then ends up negatively charged because it takes away the electrons off of your hair, and now they're on the balloon. and you bring it right up. Whoa, gosh, oh my, I can do this. I can draw straight lines. Not really, but maybe I can pretend. You bring it right up next to the wall here. Here's the wall. The wall is an insulator, which means the electrons inside, the atoms inside the wall, can't really go very many places. But it does certainly have positive and negative charges. You have positive little atoms here, which I'll draw as little circles. You know that the proton, I should said positive atoms. It's not really a positive atom. It's a neutral atom, but it has a positive charge in the center of the nucleus here. And then you have little electrons that will run around the outside edges. Here's what they can't do. The electrons can't just run all the way to the other side of the wall. That's not possible for them. But what is possible for them is that the electrons can just spend a little bit more time hanging out on the far side of their atom. So the electrons, when they see the electrons in the balloon, they say, we would very much like to get away, thank you very much. They run to the outside, to the other side of their atom like this, and then you can see that the front side of the wall looks positively charged and the back side of the wall looks negatively charged, even though it's not actually really positively charged or negatively charged. It's really truly neutral, but the electrons are just hanging out more on the other side of their atom. Notice then the positive side of the wall is facing the negatively charged balloon, and so then you get a force of attraction between the balloon and the wall, and the balloon will stick to the wall. This is very, very similar to what happens in a conductor. The only difference between polarization in a conductor and polarization in an insulator is that in a conductor, the electrons can run all the way to the side of the object, and in an insulator, they can only run onto the other side of the atom. Here's a question for you, is what would happen if my little balloon here was positively charged? Would it still stick to the wall? You say, well, yeah, Miss Wilson, it totally would. And here's why. It's because the electrons would then just hang out on the side of the atom that is closer to the balloon, like this. So the electrons would hang out over here more, leaving the front side of the wall looking a little bit negative, the back side of the wall looking a little bit positive, positive and negative. The positive from the balloon and the negative of the wall would pull towards each other, and that balloon would still stick. That's a little bit on polarization. Now, once again, polarization is actually not really a form of charging because it's not actually changing the charge on the wall. It's not actually changing the charge on the aluminum can. It's just moving around the charges within. What actually is a form of charging, though, is charging by conduction, which is our next topic. You have charged something by conduction before. If you've ever walked around on the ground, shuffled around in your socks on the carpet, you shuffle around in your little socks on the carpet, then you walk up to the doorknob and you just, oh so very carefully, touch the surface of the doorknob and you get a little shock. What is that little shock? That shock is charging by conduction. Let me show you what this looks like. I'm going to need an eraser, and I'm going to need this eraser big time. We got some serious eraser work to do. Here we go. Let's crank it up, and let's get rid of all of this polarization junk over here. Not junk, it's beautiful. We all know polarization is very, very lovely, but it does have to go, unfortunately. So peace out polarization, and on to conduction. Here's the idea. You've been walking around on the floor, on the carpet, in your socks, and that carpet has been stripping the electrons off of you, which means you are now positively charged. When you walk up to the doorknob, here is a picture of your finger, obviously. When you walk up to the doorknob, your finger is positively charged. And here is the doorknob. Oh gosh, well, that's a very, okay, yes, it's fine. It's fine, just leave it. Here's the doorknob. The doorknob is a metal conductor. So what happens is, when you bring your positively charged finger close to the surface of the doorknob, the electrons in this doorknob say, oh my gosh, look at those little positive charges over here. And the electrons run over here, leaving behind their little positively charged homes back here. This means that the little doorknob has now become polarized. The electrons that are on the little doorknob would very much like to be with the protons up here, but they can't until you touch the doorknob. When you touch the doorknob, you have provided the electrons a way of escape to your finger. So the little electrons, I'm going to change my color here slightly. Let's go with light to green. The little electrons here and here and here and here, they all say wee, and they all jump onto your finger. And that little jump of the electrons is what you feel as a shock. Now the little electrons end up on your finger here. They are no longer present. Oh, I'm going to have to crank this down because remember when I turned it up like crazy times? They are no longer present here on the surface of the doorknob. Yes, just like a true artist. Okay. They are no longer present here on the surface of the doorknob. So when you pull your finger away, the doorknob is now positively charged. Your finger is either positively charged or neutral. Either it's neutral because all of the electrons from the doorknob jumped onto your finger to cancel out all of the positive charge, or if there weren't enough electrons available on the door, then your finger might still be a little bit positively charged if there weren't enough electrons to cancel it out. So that is the story of how charging by conduction works. Notice your finger started out positive and it gave the doorknob a little positive charge here. Meanwhile, the doorknob attempted to neutralize the charge that was on. Oh gosh, oh my. Go away, Nick. Oh gosh. Why am I forever stuck at eraser mode? Can I go to a pen mode, please? Okay, well, that was awkward. Oh, am I just continuing to do great damage? Oh no, is this thing not working? Okay, please hold. Please hold, everybody. Okay, we are back in business. Here we go. Got it all fixed. So, I totally lost my train of thought though, and darn, that's a bummer. Okay, but here's the main idea. Is this is charging by conduction. Notice, charging by conduction can only happen, as the name implies, with a conductor. Can only happen with a conductor. You need something that is very, very willing to give up its electrons in order for this thing to work. If that doorknob is holding onto its electrons so tightly and it says, no, they do not have free reign, then it will not give up its electrons, and so it can't be charged by conduction. It can't be charged by touch. Here's another example for you to look at. Let's suppose that you went over to, whoops, let's move this down a little bit. Let's suppose that you, why can I not get to the eraser setting? Okay, let's suppose that you went over, you played on the carpet in your socks for a little bit, but this time the carpet gave up electrons to you, so you ended up negatively charged. Well, what would happen to this little doorknob here? Could you still charge it by conduction? You say, well, sure I could, Miss Wilson. Here's what would happen is that little doorknob would become polarized when I bring my finger near. The negative charges would run to the other side, leaving little positive charges on this side. Then, when I touch the doorknob, the little electrons in my finger see the little protons over here, and they say, wow, that looks so fun. Can we please go hang out with the protons? Because negative charge likes positive charge. And the conductor here, this little metal doorknob, says, well, yeah, we are pretty free reign here in our parenting style, and we allow electrons to come and go as they please. Yes, little electrons, please come hang out. And so the little electrons would all jump over onto the doorknob like so. And when they all jump over onto the doorknob, then you'd end up with some negative charges over here. When you pull your finger away, when it's no longer here anymore, oh gosh, nope, please, can I have a eraser setting? Okay. When it's no longer here anymore, now this metal doorknob now has an excess of negative charge, and so we say that the doorknob is negatively charged. Notice when we charge by conduction, if your finger is negatively charged, that doorknob's going to end up negatively charged. If your finger is positively charged, that doorknob is going to end up positively charged. Notice also that that doorknob is willing to give up electrons to you. It's also willing to accept electrons from you. That's charging by conduction. The last type of charging is charging by induction. Now, charging by conduction happens, oh no, don't do that please. Charging by conduction happens kind of like all the time, casually. Like you get off the trampoline and you accidentally shock your younger brother, like that just happens, and that's charging by conduction. You are transferring electrons to him or he is transferring electrons to you, either way. But charging by induction, which is our fourth method of charging, is not something that happens on accident. It's something that happens very, very intentionally. I'm going to try to show you what it looks like with my aluminum can and with my PVC pipe here. So here's my aluminum can, here's my PVC pipe. Here's kind of the setup for how this would work. Here's my aluminum can. Oh, wow, this is such a mess. You're getting to see all of the just realness, the pure raw realness of this video. Okay, here we go. Here's my aluminum can, here's my PVC. here's the idea of how I would charge this by induction. What I would do is I would bring my PVC, which is negatively charged, close to my aluminum can, but not quite touching the aluminum can here with a little bit of gap in between. What you did not just see is that when I took this thing and I brought it close to my aluminum can, this aluminum can became polarized. The negative charges in the aluminum can ran to one side, the positive charges stayed where they are, so this side is positively charged, this side is negatively charged. Now, here's what I'm going to do to charge by induction. I'm going to hold this PVC close, and I'm going to take my finger and I'm going to touch the other side of the can like this. When I touch the other side of the can then becomes charged. How? Let's take a look at a diagram. Okay, here's a picture of charging by induction. Here I have my PVC, which is negatively charged. And here I have my aluminum can, which is neutral. What happens when I bring this PVC close to my aluminum can is that my aluminum can polarizes. So the positive ends up over here because it gets left behind by little electrons that run away. The little electrons run onto this side. Now, the little electrons really, truly do despise the electrons in this PVC, not to be dramatic, but they do. They are repelled from the electrons that are in this PVC, and they would love to get as far away from those electrons as possible, but they are limited by the fact that they can't really leave the can. They have no way of escape. So they run all the way to the other side of the can. That's as far away as they can get until I provide a way of escape. When I touch the side of the aluminum can, I connect the aluminum can to me, to the chair that I'm sitting on, to the world. And so then those electrons have a little place that they could go. They say, hey, let's get out of here. I'm not really liking, oh, come back. Oh gosh, no, thank you. Bye, bye, okay. These little electrons say, I'm not really loving this whole presence of this negative charge here. We're negative charges, let's just leave. And so all of these little negative charges here run down my finger or down the wire or down whatever you're using to connect this thing. They run down and into the earth. This process is a process that we call grounding because we are connecting this polarized object or charged object. Sometimes it's a charged object, sometimes it's a neutral object that's polarized. We're connecting it to the earth and allowing charge to flow. This lets the little negative charges leave and go down into the earth. So the little negative charges leave the aluminum can here like this. So they can get more space on the surface of the earth where they can be all spread out and they're not crowded next to each other and crowded next to that negative charge that's in the PVC pipe. And then this little aluminum can is left with a positive charge. This is charging by induction. Notice, I never touch the charged object to the neutral object. Also notice, the charged object that I used to charge this thing was negatively charged, but the object, my aluminum can, ended up being positively charged. It ended up with the opposite sign of the charge as the PVC. This is always true of all charging by induction sort of situations. It always involves polarization, then grounding, and a resultant charge that is opposite of the charge of the object used to charge it. Now, let's see what would happen. What would happen here if my little PVC pipe was positively charged? Well, let's find out. Let's take a little look here. Here's what would happen. Oh, this, by the way, I didn't tell you. This symbol right here, that's the grounding symbol. It just means it's connected to the ground. Okay, let's get all of this out to the way. Okay, bye. Okay, we've had a lot of erasing in this lesson today. Okay, here we go. We got some positive charge here. Well, what's going to happen is that little can is going to be polarized. So negative charge is going to run towards the PVC, leaving positive charge behind. When I connect this to the earth, when I ground this thing, now these positive charges look at the negative charges in the ground and they say, hey, come up and play. And the little negative charges say, okay, because positives and negatives are attracted to each other. And the little negatives come running up from the ground to the aluminum can to neutralize this positive charge. So the little negatives end up on the aluminum can like this. When I pull away my finger here or my wire or whatever I'm using to connect it to the ground, when I pull this away here, then all I'm left with on this aluminum can is a bunch of extra negative charges that ran up from the earth. When I finally pull this strip away too, then my aluminum can is negatively charged because it gained negative charge from the earth. Notice that I used a positively charged PVC to charge this thing by induction with a negative charge. So induction always changes the size of the changes the sign of the charge. And those are our 4 methods of charging. Please, before you go, give yourself a nice reminder. What are the 4 methods of charging? Can you explain to yourself how each of them work, how charging by friction works, how charging by polarization, although that's really not charging, it's just moving charges around inside of an object, how that works, how charging by conduction and how charging by induction works? Then also take a moment to remind yourself, what is charge? Charge comes in 2 types. What are those? What carries charge? What does it mean for charge to be quantized, and what equation do we have for that? And that, ladies and gentlemen, is a little bit on electrostatics, charges, and charging. I'll see you next time for a little bit more on electricity. Bye, good people. Have a great rest of your day.